Online classes for students, subject physics, topic waves. This is the first unit of state syllabus of intermediate second year students. In this chapter, we will discuss about definition of wave and types of waves, equation of progressive waves, speed of transverse waves on stretched string, speed of longitudinal waves, sound waves, reflection of waves and superposition principle of wave, stationary or standing waves, resonance, organ pipes, closed organ pipe and open organ pipe, and their fundamental harmonic frequencies and overtones, Doppler effect, and finally beats. We all know something about waves. Waves may be of any type, like water waves, tidal waves, sound waves, and light waves. What is a wave? What is the definition of wave? Wave is defined as a vibration or disturbance in space. It is also defined as a disturbance in a medium. If you throw a stone in pond, then there is a disturbance created. Due to this disturbance, water waves are generated. Here, water is a medium and stone is a disturbance, and the wave generated is called as water wave. In the same way, if you speak loudly, sound waves are generated in air. A disturbance is created in air, and this disturbance is called as sound wave. Due to this disturbance, sound energy is transmitted from one place to another place. During the propagation of wave, particles of the medium will vibrate or oscillate to and fro about the mean position. The particles of the medium will not transfer from one place to another place. Only energy is transmitted from one particle to another particle and so on. Hence, the energy is transmitted from one end to another end. Waves transfer energy without transferring matter. Classification of waves. Waves are classified into mainly two types based on the medium requirement for the propagation. First one is mechanical waves and second one is non-mechanical waves. Mechanical waves are those for which a medium is required for the propagation. Non-mechanical waves are those for which there is no need of any medium for their propagation. Mechanical waves are further divided into four types. Among the four, two are based on the vibration of particles of the medium and remaining two are based on the energy and momentum transfer. Based on vibration of particles of the medium, mechanical waves are classified into transverse and longitudinal waves. In case of transverse waves, particles of the medium vibrate perpendicular to the propagation of wave. In case of longitudinal waves, the particles of the medium vibrate parallel to the direction of propagation of wave. Light waves are transverse in nature and sound waves are longitudinal waves. Next, based on energy transfer, mechanical energies can be classified into two types, standing waves and progressive waves. In case of progressive waves, the energy and momentum transfer takes place. In case of standing waves, there is no momentum and energy transfer taking place. That is, the momentum and energy in the case of standing waves remains constant. In this chapter, we will mainly discuss about two types of waves, transverse waves and longitudinal waves, along with standing waves on strings and standing waves in organ pipes. Next, longitudinal waves. In the case of longitudinal waves, the particles vibrates parallel to the direction of propagation of wave. That is, the particles moves to and fro, front and back from their mean position. Hence, they can transmit energy from one particle to another particle. In the case of transverse waves, the particles of the medium vibrates perpendicular to the propagation of wave. That is, the particles vibrate top to bottom, up and down. In this animation, we can able to see how the particles of the medium vibrates in the case of longitudinal and transverse waves. Longitudinal waves are produced in springs. If you stretch a string, if you stretch and release a string or spring, then longitudinal waves are formed. If the spring's turns are closer, then it is called as compression. If the spring turns are far away, then it is called as rarefaction. So in the case of longitudinal waves, compressions and rarefactions takes place. Sound waves are best examples of longitudinal waves. Transverse waves. If you pluck a string fixed between two ends, then a transverse wave is generated. In the case of transverse wave, crests and troughs are taking place. The light waves are best examples of transverse waves. Light waves can travel even in vacuum because they require no medium to propagate, because the light waves are non-mechanical or electromagnetic waves. Next, we can see some differences between transverse waves as well as longitudinal waves. In the case of transverse waves, crests and troughs are taking place. In the case of longitudinal waves, it consists of compression and rarefaction. In case of transverse waves, there is no pressure variation, but in the case of longitudinal waves, there is a pressure variation throughout the medium. Transverse waves can propagate through solids and on the surfaces of liquids, but the transverse waves will not or cannot propagate through gases. In the case of longitudinal waves, the waves can propagate through solids, liquids as well as gases. In the case of transverse waves, the particles of the medium vibrates perpendicular to the propagation of wave. In the case of longitudinal waves, the particles of the medium vibrates parallel to the propagation of wave. In the case of transverse waves, there is no change in density and pressure variations. In the case of longitudinal waves, there is always change in density and pressure throughout the medium. Light waves are transverse waves and sound waves are longitudinal waves. Next, the major differences between sound waves and light waves are as below. Sound waves are mechanical waves. They can travel only when there is a medium. Light waves are electromagnetic waves. They can travel without any medium. Sound waves are longitudinal waves, whereas light waves are transverse waves. In the case of sound waves, the amplitude tells about the volume, and in the case of light waves, the amplitude tells about the intensity. The frequency in the case of sound waves tells about the pitch. The frequency in the case of light waves tells about the color. The speed of sound wave is 330 meter per second. The speed of light is 3 into 10 to the power of 8 meter per second. So we can easily say that the velocity of light is much greater than the velocity of sound. Next, sound waves travel faster in most solids, but in the case of light waves, they travel slowly in solids. The best example that light waves are the waves which higher speed as compared to the sound waves. When lightning and thunder happens, we can hear the thunder a few seconds after lightning, because the light waves can travel faster and sound waves, the velocity of sound waves is less than the velocity of light waves. So we can hear the sound waves after the lightning. That is, we can hear the thunder sound after the lightning. Next, spectrum of sound. Spectrum of sound is nothing but the frequency range of sound waves. Based on frequency, the sound waves are classified into three types. First one is infrasounds, and second one is audible range, and third one is ultrasounds. That is, the frequency of sound ranges from 0 Hz to 10 to the power of 10 Hz. So we can classify sound waves based on the frequency into three types: audible, ultrasonic and infrasonic sounds. What is meant by audible sound? Sound waves of frequency ranging between 20 Hz to 20 kHz are called as audible sounds. That is, we can able to hear any sound. It may be a musical sound, or it may be a voice sound. It may be of voice. The frequency range is between 20 Hz to 20 kHz. Sound waves lying outside the audible frequency range remain inaudible to us. That is, the sound waves having frequency less than 20 Hz are called as infrasonic sounds, and sound waves whose frequency is more than 20 kHz is called as ultrasonic sounds. We cannot able to hear the infrasonic sounds and ultrasounds. The bodies which are generally smaller in size produces ultrasounds because they undergo rapid vibrations due to their smaller size. In the picture, we can able to understand that the elephants communicate using the infrasonic sounds, whereas the bats emits ultrasonic sounds. In the case of volcanic eruption, infrasonic sound waves are generated, or under compression of quartz crystal we can able to produce ultrasounds. In this picture we can able to distinguish the frequency ranges, that is infrasounds 0 to 20 Hz, audible it is between 20 Hz to 20 kHz, ultrasounds it is the frequency greater than 20 kHz. Elephants can detect infrasounds, human can hear audible sound, and bats, cat and dogs and dolphins can detect ultrasounds. A blue whale or sperm whale is the largest animal on the earth which can produce ultrasonic sounds. Next we will discuss about characteristics of sounds. Sound has mainly three characteristics, that is loudness, pitch, quality or timbre. Loudness is nothing but the amplitude of the wave describes the loudness. That is, the loudness depends on the amplitude of the wave. If the wave amplitude is very high, then the loudness is very high. If the wave amplitude is low, then loudness is also low. Next, pitch depends on the frequency of the wave. If the frequency is high, then pitch is also high. If the frequency is low, then pitch is also low. Next, quality or timbre. Quality or timbre depends on the waveform. Next, a roaring of lion is of low pitch as compared to the buzzing of mosquito. It is the best example of pitch of the sound wave. In the same way, women can speak at higher pitch than men. Next one, for example, a small baby can speak at a higher frequency or higher pitch as compared to man. Hearing ranges. Here a list of animals and their hearing ranges and their loudness in decibels. Decibel is the unit of loudness of sound and hertz is the unit of frequency. Human can hear a frequency range between 20 Hz to 20 kHz. Dogs can hear up to 60 kHz. Elephants can hear up to 10 kHz. Monkeys can hear up to 30 kHz. Cats can hear up to 50 kHz, and bat can detect and produce a frequency of about 1,20,000 kHz. In the case of loudness, if you express the hearing ranges in decibels, the human can hear 90 decibels, dogs can detect up to 113 decibels, elephants 117, monkeys 140, cat 100 decibels, bat 100 decibels. So in the table we can able to observe that the bats can produce a frequency of 1,20,000 kHz, which is the highest frequency range among the all animals. Next, in this chapter we will discuss about a progressive wave and progressive waveform. The shape of the wave is similar to the sine or cosine graph. So we can able to express a wave in the form of sine or cosine terms. Here is the various forms of progressive wave functions. First one is y is equal to a sin omega t minus kx, y is equal to a sin omega t minus 2 pi by lambda into x, y is equal to a sin 2 pi into t by capital T minus x by lambda, y is equal to a sin 2 pi by t into t minus x t by lambda, y is equal to a sin 2 pi by lambda into vt minus x, last one is y is equal to a sin omega into t minus x by v. Next, simply we can express the waveform, the displacement of any wave, as y of x comma t is equal to a sin kx minus omega t plus pi. Here y of x comma t is called as displacement of wave, and a is the amplitude, k is the angular wave number, x is the position of the wave, and omega is the angular frequency, t is the time, and pi is initial phase. And the term in the bracket kx minus omega t plus pi is the phase of the wave. Next, some basic terms in the case of wave equation: amplitude, wavelength, time period, etc. The amplitude of the wave describes about the height of the wave. If the wave is very high, then the amplitude is very much larger. That is, amplitude tells about the maximum displacement of the particle from the mean position, and wavelength tells about the distance between two successive crests, and time period is time taken for a wave to complete a wavelength distance. Here crust and troughs are the maximum displacements on positive and negative sides from the mean position. Next, we have already discussed that if the amplitude of the wave is high, then the wave height is also high. If the amplitude of the wave is low, then the wave height is also low. Next, in the case of frequency, if the wave frequency is high, then the wavelength is low. If the wave frequency is low, then the wavelength is high. That is, wavelength and frequency are inversely proportional. Here is animation describing the time period. The time taken for a particle to complete one oscillation. One oscillation consists of one crest and one trough. That is, the maximum displacement from mean position towards two extremes. So, time period is called as time taken for one oscillation or time taken for one cycle. Next, the unit of amplitude is meter or nanometer, angstroms. Wavelength unit is also meter, nanometer or angstroms. The unit of time period is second, the unit of frequency is hertz. For velocity, the unit is meter per second. For phase, it is radian. Next, wavelength. Wavelength is defined as distance between two successive crests or two successive troughs. Amplitude, the distance of crest from the midpoint is called as amplitude, or the maximum displacement of the particle from the mean position is called as amplitude. Next one, frequency. Frequency is defined as number of oscillations per second or number of vibrations per second, or the number of waves that pass at a fixed point per second is also called as frequency. Frequency is inverse of time period. Time period is defined as time taken for one oscillation or time taken to travel a distance equal to a wavelength. So time period is also inverse of frequency. Frequency is inverse of time period, so the time period is the inverse of frequency. Next one, wave velocity. Distance traveled by a wave or wave crest in 1 second or in one period is called as wave velocity. Distance traveled by a wave crest in one period is called as wave velocity. V is equal to lambda by t. 1 by t is called as frequency, so we can be expressed as V is equal to lambda into f, or V is equal to n lambda. Here n or f is the frequency of the wave. Next, phase of the wave. Phase of the wave describes the position and direction of motion of particle at that instant. Here some waves are shown in the figure. In the case of out of phase, the particles, the starting position is differ. In the case of completely out of phase, the particles' initial position is same, but the waves are in opposite direction. So it is called as completely out of phase. Next, reflection of waves at boundaries. At closed or rigid boundaries, if a wave is incidented, then the reflected wave is out of phase. That is, the reflected wave is at 180 degrees with the incident wave phase. But in the case of non-rigid boundaries or open boundaries, the incident wave and the reflected waves are same. That is, the incident wave and reflected wave are in same phase. That is, the phase difference between incident and reflected wave is 0. Next, the principle of superposition of wave. When two or more waves meet at a point in a space, then a new wave is generated whose displacement is equal to the sum of individual displacements of the waves. That is, when two waves meet, The total displacement at a point is equal to sum of the individual displacements at that point. As a result, a new wave is formed and whose displacement is expressed as y is equal to y1 plus y2 plus y3 and so on. Next, speed of waves on strings. The speed of waves on strings can be expressed as v is equal to root t by mu. Here t is the tension in the string and mu is the linear density of the string. Mu tells about the type of material and mu is also defined as mass per unit length. Mu is equal to m by L. Next one, speed of sound waves. Sound waves are longitudinal waves. The speed of sound waves differ in different material. In the case of solids, the speed of sound waves can be expressed as v is equal to root y by rho. Here y is the Young's modulus of the material and rho is the density. In case of liquids, v is equal to root b by rho. Here b is the bulk modulus. In case of gases, the speed of sound waves is expressed as v is equal to root p by rho. It is a Laplace equation and it is corrected by Newton. V gas is equal to root gamma p by rho. Here p is the pressure and gamma is called as specific heat capacity ratio. Gamma is equal to Cp by Cv. So the speed of sound waves differ with a material medium. So in the case of solids, the velocity of sound is more as compared to liquids and gases. Next, stationary waves. Stationary waves are a new type of waves. We have already learnt about transverse waves, longitudinal waves and progressive waves. Now we will learn about stationary waves. Stationary waves are formed when two waves traveling in opposite direction having same amplitude, same frequency and same wavelength superimposed, then a new wave is formed called as stationary wave. So stationary waves are formed by the superposition of two waves traveling in opposite direction. But the two waves must have same amplitude, same frequency and same wavelength. By the superposition of waves, stationary waves are formed. In the case of stationary waves, loops are generated. Due to the loops formation, at some points the amplitude is 0, at some points the amplitude is maximum. The point at which the amplitude is 0 is called as node. The point at which the amplitude is maximum is called as antinode. In the case of antinode, the amplitude of waves, two waves is added, so amplitude becomes 2a. In the case of node, the amplitude of two waves is subtracted, a minus a, that is equal to 0. That is, at antinodes, constructive interference takes place. At nodes, destructive interference takes place. Next, derivation of stationary wave equation. For that, we will take two waves traveling in opposite direction. So y1 is equal to a sin omega t minus kx, y2 is equal to a sin omega t plus kx. Here plus and minus signs denotes that the waves are traveling in opposite directions. By the superposition principle, y is equal to y1 plus y2, by some mathematical derivation, we will reach at the final equation y is equal to 2a sin omega t cos kx. Here the cos term cos kx determines the amplitude of the wave. If the kx value becomes 0, pi, 2 pi, so on, then cos value becomes 1, then we will say that the amplitude is maximum. If kx value is pi by 2, 3 pi by 2, 5 pi by 2, so on, then the cos term will become 0, then amplitude is 0. Or we can say that if the x value is the odd multiple of lambda by 2, node is formed. If the x value is natural number multiple of lambda by 2, antinode is formed. Next we will derive the harmonic frequencies in the case of stretched string. Let us consider a string of length L which is stretched between two ends, two fixed ends, and if you pluck the string, a wave is generated. It will travel from one end to another end, and at the second end the wave gets reflected and reaches the first end. So by the superposition of incident and reflected waves, a stationary wave is formed with loops. Let us suppose a single loop is formed, then the length of the string is equal to, in the case of single loop, the distance between node and node is equal to lambda by 2. So the length is equal to lambda by 2. That implies lambda is equal to 2L. By substituting this value in v is equal to n lambda, we will arrive at n is equal to v by 2L. Here v is the velocity of wave in stretched string. So we will put the value v is equal to root t by mu, which is the velocity of wave in stretched string. Then we get n1 is equal to 1 by 2L root t by mu. Similarly, we derive the equation n2 is equal to 2 by 2L root t by mu. And finally, n3 is equal to 3 by 2L root t by mu. Here the frequencies ratios are n1 is to n2 is to n3 is equal to 1 is to 2 is to 3. Next, resonance. Resonance is defined as a phenomena in which the amplitude of the wave increases when the natural frequency of any body is equal to external periodic frequency. That is, if the external periodic frequency is equal to natural frequency of any body, then the body vibrates with maximum amplitude. This phenomena is called as resonance. Resonance can be observed in musical sounds as well as in the case of tuning forks. Next, organ pipes. Organ pipes are musical instruments in which there is no strings but there is an air column. This air column generates musical sounds. In the case of strings, the musical sound is generated on the string, but in the case of open or closed organ pipes, the stationary waves are generated in the air column of the pipes. So first we will discuss the open organ pipe. Open organ pipe is one in which the both ends of the pipe is open. At open ends, always antinode is formed because the particles of the medium are free to vibrate. At closed end, nodes are formed because the particles are not free to vibrate. So in the case of open organ pipe, the stationary waves are generated as shown in the figure. If the distance between antinode and antinode is lambda by 2 and which is equal to the length of the tube or pipe, then we will deduce the equations of harmonics in the same way as in the case of standing waves on stretched string. n1 is equal to v by 2L, n2 is equal to 2v by 2L, n3 is equal to 3v by 2L. But one point is noted here that the value v is equal to root t by mu is not taken in this case because v is equal to root t by mu is the velocity of sound waves on stretched strings only. Here we have an air column, so we should not take the value v is equal to root t by mu in the case of open or closed organ pipes because the waves are formed on the air medium. Next, the frequencies ratio in the case of open organ pipes are n1 is to n2 is to n3 is equal to 1 is to 2 is to 3. That is, all harmonics are observed in the case of open organ pipes. The n1 is called as, frequency n1 is called as fundamental harmonic frequency, n2 is called as second harmonic frequency, n3 is called as third harmonic frequency. That is, all possible frequencies n1, n2, n3 are called as harmonics. Except n1, remaining all frequencies are called as overtones. So v2 is called as second harmonic or first overtone, v3 is called as third harmonic or second overtone. Next, in the case of closed organ pipe, the derivation is similar to the open organ pipe, and in the case of stationary waves on string, same derivation is taking place here, but the distance between antinode and node is taken as lambda by 4. So L is equal to lambda by 4, that implies lambda is equal to 4L. By substituting this value in v is equal to n lambda, we will get n1 is equal to v by 4L. And we can deduce the remaining harmonics in the same way. But in the case of closed organ pipe, second harmonic is not observed as well as fourth harmonic is not observed. That is, first harmonic, third harmonic and fifth harmonics are only observed in the case of closed organ pipe. So n1 is called as first harmonic frequency, n2 is called as, n3 is called as third harmonic frequency, n5 is called as fifth harmonic frequency. If you say in overtones, n3 is called as first overtone, n5 is called as second overtone. and frequencies ratios are 1:3:5. Next, beats. When two objects vibrates with slight different frequencies, we will hear a fluctuating sound, that is one soft and one loud sound alternatively. This phenomena is known as beats or beat frequency. That is, if the two sound waves are generated from two speakers having frequencies, for example 10 megahertz and 12 megahertz, the difference is very low. So due to the superposition of these two waves, a new wave is generated. In the new wave, one soft and one loud sound is observed alternatively. It is called as a beat. Next, in the diagram, we will see that the frequency of first wave is 10 megahertz and second wave is 12 megahertz. The difference is 2 megahertz. So the 2 megahertz is called as beat frequency. The difference is called as beat frequency. Beat frequency is also expressed as the number of beats produced per second. Here FB is called as beat frequency. F1 is the frequency of sound wave 1 and F2 is the frequency of sound wave 2. And next one, the applications of beats. Beats are very useful in many cases, like to find unknown frequency of tuning fork. We can able to find the unknown frequency of any tuning fork by the principle of beats. Next, we can able to tune any particular radio, FM or AM station by the use of beats. We can able to tune musical instruments to a reference pitch by the applications of beats. We can able to identify the hazardous gases in mines. It is also an application of beats phenomena. Next one, Doppler effect. Doppler effect is nothing but the variation of sound waves due to the relative motion between source and the observer. If the observer is moving towards or away from the source, he will hear a frequency somewhat lower or greater than the original frequency of sound. If the source is moving towards or away from the observer, then also the observer will hear a frequency of lower or higher frequency as compared to the frequency of sound of source of sound. That is, a change in the frequency of sound heard by the observer due to the relative motion of the source and observer. So Doppler effect can be expressed as or defined as the increase or decrease of frequency of sound waves due to the relative motion between source of sound and observer. Here F0 is the observer frequency and Fs is the source frequency. Let us consider two cases. First case is the source is moving towards an observer, and second case is source is moving away from the observer. If the source is moving towards the observer, then the sound wave length decreases as the source is moving towards the observer. It is given by lambda naught is equal to lambda s minus Vs into t. Here Vs is the velocity of source of sound. Then by some mathematical derivation, we will arrive at a final equation F0 is equal to Fs into V by V minus Vs. Here the denominator is less than the numerator, so we can say that F0 is greater than Fs. Next, if the source is moving away from the observer, then the sound wave length increases. That is, the sound wave is like a stretched spring. That is, the wavelength increases. That is, the distance between crust and crust to crust increases. So lambda naught is equal to lambda s plus delta x. Here delta x is Vs into Ts. So by some mathematical derivation, we will arrive at the final equation F0 is equal to Fs into V divided by V plus Vs. Here in the denominator the value is more as compared to the numerator, because in the numerator V is observed, in the denominator V plus Vs is observed. As a result, F0 is less than Fs. That is, in the case of in the first case, if the source is moving towards the observer, the frequency is increased. If the source is moving away from the observer, in the second case, If the source is moving away from the observer, the frequency is decreasing. Doppler effect. The difference between real frequency and apparent frequency is called as Doppler shift. Real frequency is the original frequency of sound, and apparent frequency is the frequency heard by the observer. So Doppler shift can be expressed as NR difference NA is equal to delta N, or FR difference FA is equal to delta F. Here NR is the real frequency and NA is the apparent frequency. FR is the real frequency, FA is the apparent frequency. And delta N is called as Doppler shift. Delta F is also called as Doppler shift. Next, the two cases, that is, the observer is moving towards the source, and second one is the observer is moving away from the source. We have already discussed that if the source is moving towards the observer and source is moving away from the observer, here we will learn about if the source is moving towards the observer and if the observer is moving towards the source and observer is moving away from the source. If the observer is moving towards the source, then the observer can hear more number of waves per second. That is, the relative velocity of sound with respect to observer is increased, that is C plus V naught. So the frequency is increased. It is observed in the final step, that is F dash is equal to 1 plus V naught by C into F. Here the plus V naught by C, due to the factor plus V naught by C, we will say that the frequency is increased when the observer is moving towards the source. Next one, if the observer is moving away from the source, then the relative velocity of the sound wave relative to the observer is decreased as C minus V naught. So we can arrive at the equation F dash is equal to V minus V naught by C into F. Here the factor minus V naught by C tells that the frequency of the sound wave is decreased. Next, application of Doppler effect. Doppler effect have various applications. Among them, we have some of the applications here. First one is in the aircraft navigation, Doppler effect is used. Next one, in ultrasound scanning, Doppler effect is applied in order to scan the body parts. ECG, echocardiogram, also uses the Doppler effect. ECG is abbreviated as echocardiogram. It tells about the functioning of heart. Next one, Doppler effect is also used in the study of Saturn rings. Next one, Doppler effect is used in sonar and radar techniques. Here sonar is called as sound navigation and ranging. It is used in aircraft navigation, and radar technique is called as radio wave detection and ranging. By the radar technique, we can able to detect the submarines under the sea. Next, the Doppler effect is also used by the traffic police to check the speed of vehicles. Here Doppler radar technique is used to calculate the speed of the vehicle. Doppler effect is also used in weather forecasting, that is, weather changes can be detected by the application of radar techniques. And in medicine, the Doppler effect is used to identify the blocks in the blood vessels. The Doppler effect is also used in astronomy. If the light coming from a distant star is of higher wavelength, then it is called as redshift. If the light coming from distant star is having lower wavelength, then it is called as blue shift. Redshift tells that the universe is dynamically expanding, and blue shift tells that the universe is compressing. But the scientists researched about these shifts, Doppler shifts, and they arrived at the result that there is a redshift taking place. Due to the redshift, the universe is ever expanding dynamically. So the Doppler effect has various applications, starting from medicine to astronomy. That is about the Doppler effect and cases and their applications. This is about the chapter wave, the first unit in the intermediate second year syllabus of state syllabus. Thank you one and all.